Have you ever stopped to think about what a camera flash, a life-saving defibrillator, and even the cells inside your own body all have in common? Well, the answer is this tiny but incredibly powerful component that can store and release energy in, well, a flash. So let's dive into the amazing world of capacitance. But before we get into the nuts and bolts, just take a look at this. It's this beautiful, complex pattern, and it's completely frozen inside a block of acrylic. So what do you think we're looking at here? Some kind of fossil? A piece of modern art, maybe? What you're actually seeing is something called a Lichtenberg figure, and it's pretty much fossilized lightning. It's the exact path an electrical discharge burns through the material, which, you gotta admit, brings up a really cool question. How in the world do you bottle lightning? Now, while we can't literally bottle a thunderstorm, we have invented a device that does something remarkably similar, just on a much smaller scale. And that brings us to the hero of our story today, the capacitor. So what exactly is it? Well, the simplest way to think about a capacitor is like an energy bucket, but for electricity. Its whole job is to grab onto an electrical charge and then, when the time is right, let it all go at once. And at its heart, it's just two conductive plates with an insulator sandwiched between them. That's it. And here's how it works. It's actually pretty straightforward. When you hook it up to a battery, positive charge starts to pile up on one plate and negative charge piles up on the other. Now they're super attracted to each other across that gap, but they can't cross. So instead, all that energy gets stored up in the electric field between them, just waiting. And the size of this energy bucket, we measure that with its capacitance, which we represent with the letter C. This little formula right here just tells us that capacitance, C, is how much charge, Q, the thing can store for a certain amount of voltage, V. So, more capacitance means you can pack in more charge at the same voltage. Simple as that. Now, the unit we use for capacitance is the farad, and it's named after the absolute genius Michael Faraday. You'd probably think, okay, 1 farad, that's a pretty standard amount, right? But in the world of electronics, 1 farad it's just massive, absolutely enormous. And this quote just perfectly illustrates how ridiculously huge a farad really is. To build a basic 1 farad capacitor, just 2 metal plates separated by a tiny bit of air, each plate would need to be 10 kilometers. That's about 6 miles on each side. I mean, you'd have to build a capacitor that's bigger than a city. It's wild. And yet, here are the capacitors we use every single day. They're tiny. Some are so small you can barely see them. So how on earth do engineers manage to shrink a city-sized component down to something that fits on the tip of your finger? Well, the answer lies in a secret ingredient, a special material that gives the capacitor this huge boost in its storage power. It's something called a dielectric. A dielectric is really just an insulating material. It could be plastic, ceramic, even paper, that you stick between the capacitor's plates. But it's not just a spacer. When it sits in that electric field, its molecules all line up and create their own weaker electric field that pushes back. And that little pushback makes it way easier to pack more charge onto the plates. So here's the bottom line. Adding that dielectric lets the plates store way more charge at the same voltage. The better the dielectric, the bigger the boost. We measure that boost with something called the dielectric constant, or kappa. A high kappa means you get a much, much higher capacitance without needing any more space. And this whole dielectric boost thing allows for some really clever compact designs. For instance, a lot of common capacitors are made of these long, thin sheets of metal foil and a dielectric film, all rolled up together like a jelly roll so it can fit into a tiny little can. It's genius, really. Of course, capacitors rarely work by themselves. They're total team players. They're essential building blocks that engineers can combine in circuits to get all sorts of different effects. So there are 2 main ways to connect them: in series, where they're lined up one after another like a train, or in parallel, where they're side by side like lanes on a highway. And here's the key difference. In series, every single capacitor has to hold the exact same amount of charge, but in parallel, each one has to have the exact same voltage across it. And those different connections lead to totally opposite results. When you connect capacitors in parallel, it's easy. Their capacitances just add up. You just get a bigger total energy bucket. But, and this is where it gets a little weird, when you connect them in series, the total capacitance actually becomes smaller than the smallest single capacitor in the whole chain. It's pretty counterintuitive, right? Okay, so we've got the theory down, but why does any of this actually matter? Well, it matters because this simple ability to store and release energy is the invisible force behind, well, so much of our modern world. Take this, an automated external defibrillator, or AED. Inside that box, a big capacitor charges up to a really high voltage. Then, when the button is pushed, it dumps all of that stored energy in a split second, delivering this powerful, controlled shock to restart a heart. I mean, this is literally a life-saving application of capacitance. Or how about an old-school radio? Ever turn that tuning knob? When you do that, you're actually adjusting a variable capacitor inside. By changing its capacitance, you're letting the circuit tune into one specific frequency, your favorite station, and filter out all the other noise. And if you look really closely at any circuit board, I'm talking your computer, your phone, anything, you'll see dozens, maybe hundreds of these little guys, often marked with a C. They are the unsung heroes, acting as tiny energy reservoirs, smoothing out power, filtering signals. All of our microelectronics just wouldn't work without them. But here's the part that really blows my mind. Nature figured this out first, a long, long time ago. The membrane of every cell in your body separates positive and negative ions. It is effectively a tiny biological capacitor. This is the fundamental principle behind how our entire nervous system sends signals. It's incredible. So, from the life-saving spark in a defibrillator all the way down to the spark of life itself, this principle of capacitance is absolutely everywhere. It's such a humble concept, right? Just two plates and a gap, but it powers our world and it powers us. It really makes you wonder, what can't they do?